Welcome! This video provides a brief introduction to two-dimensional graphics, the way the computers represent them, and the kinds of file formats that are used to store them. So, to represent anything, a computer needs to reduce it to numbers. And for graphics, there are two main ways of doing this. We can store graphics as vector-based graphics or as bitmap-based graphics. So, the big difference is how they're stored. Vector art is stored as a bunch of mathematically defined curves and lines, and then descriptions of how to fill those. And so maybe we'd say that, okay, inside the area defined by that curve, and this arc and that arc, we're going to shade that with this dark yellow. Vector graphics, because they store mathematical descriptions, are very good at scaling. You can scale these descriptions up to very large sizes, and you don't get blocky, weird-looking images. What they're not good at is showing photorealistic patterns. Right? They're good at solid blocks of color, at gradients, like in this flower where we possibly go from like a dark pink to a lighter pink over a defined space. That's the kind of coloring that they're good at. You see vector graphics a lot in Flash-based games. Flash works well with vector images. Also, if you do graphic design using something like Adobe Illustrator, you're working with vector graphics. The other kind of art is bitmap art. And bitmap art stores a picture by breaking it into little squares, called pixels, and storing a color value for each pixel. And those colors will represent numerically, so each pixel turns into a number that represents its color. When we're talking about bitmap art, we care about how many pixels are in the image, kind of its width and its height. And then we also care about how many colors are used for each square, how much bit depth we have, how many different possibilities we have to represent each little square. The modern standard is 24-bit color. And so that means each pixel in the image has 24 bits, or about 16 million different choices. It used to be the case that 8-bit color was pretty popular. If you've ever heard of 8-bit games, it's one of the things they're referring to, is an 8-bit color palette where there's only 256 different colors. And if we have to represent the same information with fewer choices, we end up with things like, well, I can't represent this nice dark blue to lighter blue transition, so we have this dithering, this blocky kind of light blue, dark blue pixels just thrown next to each other to try and simulate a medium blue. The same amount of information, 256 gray levels, is actually enough to represent a near photorealistic picture that goes from bright white to dark black. And the lowest possibility would be 1 bit, where each pixel's only got 2 choices, either on or off, black or white. Now, for an actual image, when we take that information, we store it in a file, we have to store those numbers, those pixel values, in some format. And there's multiple ways that people have come up with for doing this. The formats you should really be aware of are JPEG, GIF, BMP, and PNG files. So a GIF file only stores 256 colors per image. Kind of one thing to be aware of if you're storing something as a GIF, you can't have photorealistic color. Now, if you're working with a small image that doesn't have a whole lot of colors, you could have 256 shades of blue if that's the only color you're using, which would probably give you all the blues you could possibly care about. But if you're talking about something more complex, like this hot air balloon picture, you're going to run into problems. What GIFs do well is you can have transparency. And so that was their claim to fame on the web for a long time. And they can be animated. And we've seen a modern resurgence of animated GIFs in little movie clips compressed into an image file. JPEGs are most popular for representing photographs. If you take a picture on a cell phone, or if you take one with a digital camera and you're not using a very super high-end camera, you're going to get a JPEG file out of it. These can represent photorealistic color, 24 bits. They can't do animation, they can't do transparency, and they compress the files using what's called lossy compression, which means that every time you save the file, it throws away a little bit of information to reduce the size. And it does this with some tricks that hopefully aren't noticeable. But over time, if you keep opening the same JPEG file up, editing it, saving it again, you're going to get a worse and worse and worse looking picture. So it is something to be aware of. JPEG is a nice format for kind of a final version of artwork, but you don't want to have your working artwork ever be stored as JPEGs because of this issue. PNG files, PNG files, portable network graphics, are 24-bit, so like JPEG, they can store a very wide range of colors. They can have transparency, and unlike GIFs, which can have one transparent color, PNG files can have partial transparency. So you could have like a black cloudy area under a character that is partially transparent and looks like a shadow on top of whatever you place that character on. So if you put them on top of grass, you'd see kind of little darkness covering the grass, but you'd be able to see the grass through it. PNG files do not have any native animation ability. So GameMaker, this is the format GameMaker likes to deal with, and if you try to save an animated sprite from GameMaker, it just saves it as a strip, as a series of images placed next to each other. In the final format, BMP file, this is an uncompressed file format. If you have an image and you want to be able to work with it and not lose quality over time, you'd want to either be using a BMP file, a PNG file, PNG file, or some other more advanced format. Now, those bits that we use to represent the individual pixels go to describe the color. And there's actually multiple ways we can describe color, but the predominant method for computers is additive color mixing. That's where we take red, green, and blue values and mix them together. If we don't have any red, green, or blue, we have nothing, we have black. If we have all red, all green, all blue maxed out, we get white. And if we have green and red, we get yellow, blue and green make cyan. Different mixtures of the colors produce different, of those three primary colors, make different colors. To get something that's gray, we just mix them in equal proportions. Anytime you use a program and you go pick colors, that'll probably be one of your choices, to pick red, green, and blue values. And assuming you're using 24-bit colors, you'll get to pick a value between 0 and 255 for each of those color channels. Why that? Well, because that's 8 bits gives you 256 different choices. So we can store 0 to 255 as an 8-bit number. And remember that what we have is 24 bits total. So you divide the 24 by 3 colors, we have 8 bits for each color. So hence the value 0 to 255. Now that's not the only way to represent colors. I can take a color like this kind of limey green that's got a red, green, and a blue component, and instead I could represent it as a hue, saturation, and luminance, or brightness. So on this scale, the hue is the basic color, the saturation is how much that color there is, and the brightness is basically how far away from black we are. So we can use that recipe to come up with the same exact color as we can come up using a red, green, and blue model. It's worth knowing about the different models. Like I said, usually if you go pick a color, you'll probably be picking it as red, green, and blue. But there's some modifications to colors that are easier to make using these sliders. If you just want to make something darker, it's a lot easier to think about reducing the brightness or the lightness than it is to think about how to modify the red, green, and the blue to get a slightly darker version of the same exact color.